All right, let's just jump right into this explainer. Today, we're putting on our lead systems engineer hats to architect a modern time series data pipeline. If you're a software or data engineer who's completely tired of wrestling with out-of-memory errors from vehicle telemetry, dealing with overly complex data modeling, or struggling to write functional real-time alerts, well, this hands-on architecture review is exactly for you.
To really ground this engineering challenge right from the start, just think about this scale. A modest 1,000 vehicle fleet generates an astonishing 500,000 metrics every single second. We're not just talking about a trickle of standard API calls here. This is a massive, unrelenting fire hose of sensor data. If your database schema isn't perfectly tuned, that sheer volume of write amplification and I/O bottlenecks will just completely overwhelm your traditional infrastructure.
So here's our roadmap for this explainer. We're going to structure this as a complete data pipeline walkthrough. We'll start with the core telematics challenge, build out our time series architecture, dive into TCU edge processing, run some actual multi-stream correlations using SQL, and finally wrap it all up with scaling operations and ROI. Let's get to it.
Part 1, the telematics challenge. We really need to understand exactly why forcing modern vehicle data into traditional relational databases causes them to completely buckle.
Look, relational schemas are great, right? But they're optimized for discrete transactions. They simply cannot handle 500,000 continuous inserts per second. Try forcing that high-frequency insert and update pattern into MySQL or Postgres, and you're going to see lock contention, spike, severe index bloat, and storage costs that just absolutely skyrocket. Time series DBs, on the other hand, use highly optimized columnar storage and inherent time ordering to handle this exact workload effortlessly.
And it's not just the sheer velocity. It's the variety. We are mapping 11 totally disparate telemetry sources here. You've got everything from event-based string data, like ADAS collision warnings, colliding with continuous numerical floats from OBD-II diagnostics and TPMS sensors. Trying to normalize all of that into a rigid, traditional schema? Yeah, that creates an engineering nightmare of nullable columns and overly complex ETL pipelines.
All right, part 2, time series architecture. Let's see how specialized ingestion protocols completely eliminate those exact bottlenecks. So, unlike relational rows, InfluxDB is built entirely around time. This enables millisecond-scale ingestion and massive storage compression, basically because timestamps increase monotonically. With InfluxDB line protocol, mapping those disparate sources is actually seamless. The syntax is super straightforward. You lay out your measurement, comma, your indexed tags, space, your unindexed fields, space, and finally a Unix nanosecond timestamp. This highly structured, time-ordered format literally lets the engine's compression algorithms shrink your storage footprint by 80 to 90%. Huge savings.
Now, to avoid those dreaded memory bloat and OOM errors, we have to be ruthless with our cardinality strategy. As developers, getting this data modeling right is literally everything. If you try to index highly volatile data, like a rapidly changing RPM or a fatigue score, your index cardinality just explodes, and boom, your database crashes. So here's the rule. Identifying metadata that you actually filter by, like vehicle ID, fleet ID, or driver ID, those become your index tags. The raw, high-frequency telemetry, like battery volts or fatigue score, those stay as unindexed fields.
Moving right along to part 3, TCU edge processing. Because before any of this data even hits our cloud architecture, we've got a massive bandwidth problem to solve. Streaming raw 100 Hz data straight to the cloud is a fantastic way to bankrupt your project on bandwidth costs alone. Enter the Telematics Control Unit, or TCU. Think of it as a mobile analytics engine acting as a critical pre-processing layer right at the edge, literally inside the vehicle backbone. It intercepts all those raw signals from the engine, the dash cams, and the tires. It even uses Edge AI to process heavy visual scene data into simple, lightweight metadata, sending just the classification and confidence scores instead of gigabytes of raw video files.
This edge pre-processing creates a beautifully efficient pipeline. Those raw 100 Hz sensor streams, the TCU aggregates them into 5-second windowed averages before they ever leave the vehicle. By the time that data hits your HTTP API or MQTT gateway, it's already structured, filtered down to a manageable 0.2 Hz, and perfectly formatted for InfluxDB. This edge optimization is exactly how we guarantee that when you run a cloud query, your response times stay well under 10 milliseconds.
Part 4, multi-stream correlation. Once that data is ingested, it's time to put our SQL skills to work and temporarily align these disparate streams for real-time alerting.
Because everything is aligned on exact millisecond timestamps, we can write some incredibly powerful SQL logic. Let's break down 3 real-world functional queries. First up, the slow leak alert. You can use a date trunk function to bucket TPMS pressure trends over a 7-day window. If your where clause catches a drop of more than 2 psi per week, boom, trigger a webhook. Next, fuel theft detection. We write a fast temporal join here. Monitor high-frequency fuel levels for a sudden 10% drop in under 30 seconds. Join directly with GPS data where vehicle speed exactly equals 0. Finally, incident reconstruction. We'd write a sub-second query joining driver monitoring system fatigue scores greater than 70 with ADAS collision warnings greater than 0.8. Group those in a rolling 5-second window on a normalized timestamp axis, and you instantly expose the root cause of a crash.
Now, historical trends are absolute gold for predictive maintenance, but you can't keep raw data forever. So as an architect, you set up automated continuous downsampling tasks. You keep those high-frequency, millisecond data points in a 30-day retention bucket for immediate forensic queries. Meanwhile, automated SQL aggregation tasks are running in the background using group-by-time logic to summarize that data into hourly trends, writing it out to a long-term retention bucket. This lets you query multi-year trends affordably, without scanning petabytes of raw data and melting down your system.
And finally, Part 5, Scaling Operations and ROI. We've built an amazing architecture, but as technical leads, we still have to justify these infrastructure choices to the business stakeholders.
Let's translate our schema and queries into hard dollars. By knocking down data silos and enabling this predictive multi-stream correlation, fleets are seeing massive operational efficiencies. We're talking an 8 to 15% improvement in fuel efficiency alone. And when you can actually run sub-second queries on your telemetry, you unlock a 15 to 25% drop in maintenance costs. You find that slow leak before it becomes a highway blowout. Plus, those real-time safety queries we just discussed for fatigue and ADAS, they drive a staggering 25 to 45% reduction in accidents and claims. For most organizations, all of this results in an ROI payback period of just 1 to 2 years.
The absolute best part, this architecture scales linearly. Whether you're tracking 250 vehicles or 1,000, your database doesn't need to be totally re-engineered. But the financial savings grow exponentially into the millions. For a regional fleet of just 250 vehicles, proper time series tracking yields about $280,000 in annual savings. Scale that up to a national fleet of 1,000 vehicles. And because our cardinality and retention strategies keep cloud costs completely flat, the business pockets a massive $4.68 million in operational savings.
So, as modern vehicles basically become rolling data centers, you really have to ask yourself if your current database architecture is actually prepared for the future of fleet intelligence. We've just seen how strict schema cardinality, intelligent edge processing, and time-bucketed SQL queries can turn a 500,000 metric per second fire hose into actionable, life-saving alerts. Take a hard look at your own pipelines today. Are your systems just hoarding terabytes of dead data, or are they engineered from the edge to the cloud to extract millisecond insights before a breakdown even happens?